So we gotta, we're doing this, right? You're writing? So the radius is clearly the height of the curve, but I need a radius squared, right? Teddy, you got the idea what's going on? Yep, nice. I don't know. Can I do infinite limits on Desmos? Yeah? Nice. What a cool. It, right? Yeah. Yeah, INF. Nice. That's sweet. So sweet. How do we ever use these stupid things? I don't know. Yeah. Uh-oh. We got a different number. What did I do wrong? Anybody get a different answer than me? Huh? Oh, I see what I did. Mm-mm. Oh, yeah. It's a, no, it's a 4x, that's right. Anybody get a different? Anybody get different than 5 pi over 4e squared?
Oh,
You see it?
it does most you multiply your answer by 5.
Oh, nice. Ha, ha. Thank you. What would I do without you? Ha, ha. So how'd you do? What am I expecting to see? I'm expecting to see you write it as a limit I'm expecting to see you use L'Hopital's rule, the disk method, right? So I'll give you something like that today. Everyone okay? Ryan, you all right? Yeah, so just me talking through it. Right, I've got the curve. I know I'm rotating around the x-axis. I'll give you the hint, use the disk method. So I get the radius, which is just the height of the curve, and I square it, right? It turns into the problem just like the second problem on the test, right? Just with a little bit of a change. I use the shortcut to get the integral. But more important, I write it first as a limit before I do that. And then I like to evaluate at 1 first and then have my limit second, right? And then I'm just claiming I'm doing L'Hopital's rule. I don't, it's a Calc 1 thing, so we know we have infinity over infinity there. Take derivatives until we get to something we can evaluate. And then, of course, I check it on Desmos. And if I made the mistake I made right here on the quiz, I'm freaking out, right? And then what am I doing? I do it over. And then, but what was my only mistake? I didn't copy the integral right into Desmos, right? So you got to be careful because it's really subtle, easy to make mistakes. What else can I do? Excuse me. Anything else you want me to answer this morning? All right, let's look at a problem on, here is a problem on a Calc 2 test I've given. We want to show that this thing is positive is obvious, right? All my terms, pardon me. All my terms are positive, right? That's pretty obvious, yes? Yeah. And so we just want to show that it's decreasing. So we've got the series from n equals 2 to infinity. N squared plus 2n plus 5. Right? So how do we do that? Say it again? It looks like it's going to be a complete the square problem, but how do we show it's decreasing? So there's two ways. One is the way I've talked about already, right? Take a derivative, show after 2 that the derivative is negative, right? Or I could show this. I think the derivative is easier, but this is an option if you somehow forgot how to take a derivative. Doubtful, right? So the two options there. I could show that a term is bigger than the very next term, right? So your choice on the exam for sure. Let's do them both now. So I'm going to cross multiply, right? Should be greater than, sorry. Pretty easy to show that. How are we doing? Yep. Say again? Oh, the derivative of the inside. Yeah, I did just the chain rule. Yeah. Yeah, it could be done with the quotient rule, right? The upstairs function is 1, the derivative is 0. The downstairs function is x squared plus 2x plus 5. The derivative is 2x plus 2. And divided by that downstairs squared, right? So yes, I could use the quotient rule. Nice. So now I know it's always positive and decreasing. I can use the integral test to, to tell if it diverges or converges. So on your market set, go. So the integral from 2 to infinity of 1 over x squared plus 2x plus 5 dx. I'm not doing it. You can't copy me. Go ahead. Yeah, yeah, right. So we're just doing that limit, right?
Like, I knew that was the case, but I didn't know if you had to do something fancy.
No, no, not at this point. Because we did all that stuff in Calc 1. So at this point, we can look at a graph and just say what the limit is. We know, right? Yeah, I don't think I did it any different in Calc 1. When just looking at the limit of arctan, right? We know what height it's getting to. And of course, I could just call the inside x, right? I don't have to call it a plus 1 all over 2. Like, yeah, yeah. I guess it's just getting there slower, right? Y equals arctan of x, or y equals arctan of a little bit of a smaller x. Just takes a little bit longer to get there. But they still both get the same place. How'd you do? Ryan, what? Yeah. Yeah, it happens. So, but what do you want to remember what you want to do when you're taking the test, right? Or when you're working, is you want to make sure you're at work and you're working with a chemical or whatever, right? So look at my first thing I did was right, I just graphed that downstairs function to tell whether or not I should use partial fractions or complete the square, right? Really no other option for me. And then once I complete the square, I want to make sure. So a quick way to tell if I did it or not is just now graph your complete the square and see if it's the same curve, right? Or FOIL back the square and make sure, right? Say it again. Yeah, so but once we have but remember, if I have that square root downstairs, I'm thinking arc sine. If I have just 1 plus u squared, I'm thinking arctan, right?
When I saw the mark down there, I'm like, wait a second, is that, yeah.
Yep. So you got to have this kind of you got to allow things to change. You got to allow things to turn into another problem, and keep your cool about it, right? And what do you do if you right you plot two things and they don't match? Then you know you have it wrong. So, that's when the panic could set in, or when you just go, okay, wait a minute, I probably just made a simple error, right? Or what happened here? But I mean, clearly, you can see everything from the first test is coming into play. You have to know the stuff from the first test. Teddy, were you taking a picture? Do you need another shot of? You got it. All right. Anybody get there all the way? Brian, yeah? Brian, did you get there? Nice. Teddy, Noah, close?
Yeah.
Yeah, you got there? You got there? No?
I didn't finish the electrical. I was like finishing up the.
That's fine. Yeah, I know I'm too fast. Believe me. I got up at 7:20 today. I drove very fast to get here. It's not, you know, so I'm trying to give you space to do things, but I know I go too fast when I'm solving a problem, but hopefully you're going to redo it, right? You go home and you do it over. Nice. Let's recap something we did yesterday with my power series. I do have other tests, so I will give you another test. Don't worry about that. Let's take a look at number 6 here. So just kind of recapping everything we've done. So find the power series representation shown here, right? So f of x is 1 over 1 plus 2x quantity squared. So if I give you something like this, and I'm going to, it's either take a derivative or take it, do the antiderivative, right? It's going to be one or the other. It's not a choice. It could even be take the derivative twice or the antiderivative twice. And then when you're done, you have to, right? You have to inverse operate and get back to the original. But remember, this is the one that should help you, that if y is 1 over x, y prime is negative 1 over x squared, right? So I'm seeing I have to do the antiderivative, right? And then get the power series rep, and then take the derivative. Yes, you with me? Good. On your mark, get set, go. Anybody get to this box yet? Okay, keep working. Oh, sorry.
No, can't see
Yeah. Oh, I'm sorry. Is that better?
it. Yeah.
There's the final answer. You might have n minus ones or, yeah? You know, I'll talk about that. Your answer's still right, but I'm trying to, at the end, see if I can replace things to clean it up as much as possible, right? It depends. So, yeah. So but you want to, if you can get it to say x to the n, do it. If you can't, no big deal. I don't care too much about it. If you get it there, I'll be fine with it. But the thought is, and let me know if this is so. So if we didn't change anything, we get to here. Does that look? Anybody get there? Should I talk through the whole thing?
When did the negative one get plus?
When I brought in that -1 from the -1/2 out here, so I bring in a -1 at,
Oh, okay.
right? So let me talk through the whole thing, okay? And then I'll talk about cleaning up the exponents or the ends. So first of all, when I get my test and I get this problem, I'm going to remember, or I have on my notes, that I either have to, if I can't go directly into my little formula, right? If I can't go directly into that, then I know I have to either take a derivative or an antiderivative. Okay, so we figured that part out. So I'm taking the integral of f of x dx, and I see it's a u sub, right? There's clearly an inside. So u is 1 plus 2x, so du is 2 dx. So I multiply by 2 and I cancel with the 1/2. And then I have my u sub. Yes, you with me? No, that's okay to see?
Yes.
So then I take the integral, right? I take the integral, so it's a power rule. Hey, come on in.
Are you in here able to go to the network, the internet?
Yes.
You are.
Wait a minute. Let me check. Oh yeah, it's just on Desmos. Yep.
On these desktops, you're able to get to the network?
Everyone's. Yep.
Okay, because I wasn't sure if it was like the whole, everything, but, did you look at your phone real quick? to see-
I don't have a phone.
No, I mean, the college.
Yeah.
Go ahead.
College. Oh, that-
Okay. This is this is networked. This is part of the college network.
Yeah.
It's dark, so apparently it's not everything. Sorry to bother you.
No problem. So it's a power rule, right? So I add 1 to the power, divide by the new power, right? Simplify. And I'm reminding myself that I still have the integral of f of x dx. And so there it is. So when I finally get that integral done, there it is. Do I care about the constant in this case? No, right? So then I see I have something that looks like what I want. Remember what I want, right? And so I see that I'm going to put in that -2x into my summation notation, into my series. So far, okay to here? All right, so now I want to simplify. I want sine coefficient x term, right? So I still have the -1/2, and then the sine plus or minus the coefficient, the x term. But I can bring in the -1, so that's an extra power of extra factor of a -1. So the -1 goes to n plus 1. Another factor of 2, but in the denominator, so I'm going to lose a factor of 2, so n minus 1. And that's a pretty good spot to get to, right? Pretty damn good, because then all I have to do now is take a derivative, right? So now solve for f using the fundamental theorem of calculus. What the hell is that? Well, derivatives and antiderivatives undo each other, right? So I take the derivative. Sorry, I put my notation in and then I'm going to take the derivative. What happened to my integral? They cancel, right? They cancel. So then I take the derivative. Notice the -1, nothing changes about the -1, nothing changes about the 2, but when I take a derivative of x to the n, it's n times x to the n minus 1. And then I want to start writing out terms to see if I have anything that can just be skipped. And clearly when I put in the n is 0 into n, that first term goes away. So this first term is 0. I don't need to have it in my notation. The second term is good, right? It's a 2, right? 2. 2 times 1 times x to the 0. X to the 0 is 1 for us now. All this, we've been fighting you so long about x to the 0, right? Probably since 8th grade, maybe 9th grade. You can't have x to the 0 if x is 0, right? This is one of the indeterminate forms that we handled with L'Hopital's in Calc 1, but now we're saying, hey, okay, just let it be 1. Sometimes it can be 1, sometimes it's not 1. In this case, let's just let it be 1, so that we have always convergence at the center. So the second term is good. So I think I might be able to clean things up. Since I can't start at 0, but I can start at 1, what if n minus 1 was just n? Right? What if n minus 1 was just... So if I put 1... So here's... I'm sorry. If I put 0 in here, it was no nonsense. If I put 1 in there, it's okay. So if I started just at n, I can start again at 0. So if n minus 1 becomes n, what did I do to n minus 1? What did I do to n minus 1 to make it an n? What did I add to it? 1. So if I'm going to add 1 to n minus 1 to make it n, if I take n plus 1, it becomes n plus 2, but that's the same as, because that's on my -1, right? That's on my -1. I wanted to start... what sign did I get here on my first term? I wanted to start at positive. It's the same as starting at 0. N plus 2 is the same as n, because they're both, right? If they start at 0, they're both even. I know that's confusing a little bit, but then what happens to n? What happens to n? N becomes n plus 1. Right, because I'm just adding 1 to everything. So, but look how clean it becomes. I mean, not that big of a deal, right? But it's just how I'm trying to look at it. I'm trying to make things as, it's in quotes, pretty as possible, right? Nice. Pretty massive problem, isn't it? It's long. It's complicated, right? So you've got to practice. You've got to make mistakes. You've got to ask for help. Okay. You have to do some research. You've got to perfect your formula sheet. Yes, it should be have everything down. Every problem you came up with when you're practicing should have a fix on your formula sheet. Oh, when this happens, make sure you look for this, or et cetera, right? Okay, anybody need pictures? No? Okay. Make sure you do them over. All right. Let's do one. Let's say it again.
the radius of convergence.
Oh, radius of convergence, yeah. So now we have f of x. We can find the radius of convergence looking at that ratio test. So write this version down, and let's do the ratio test. Yeah, 1/2. Nice. Any part in there a little confusing or? No, is that okay?
Yeah, I got it.
What did I skip in the first part? What did I skip?
The negative.
Negatives. I know they're going to cancel. I'm just a little lazy today, right? So then I simplify and I get down to here where I realize, right, I've got infinity over infinity, right? So I just, it's a Calc 1 thing. I don't have to do that. I know that as n goes to infinity, that limit is 1. And what about this line right here? How did I go from here to here? Yeah, so from this thing, once I'm working on this limit of the absolute value of 2x, but as n goes to infinity, so there's nothing to do, right? So I know my limit is absolute value of 2x, and I want that thing to be less than 1, right? Because of that whole geometric thing, x times, right? Every time I'm multiplying by x, right? I know it's going to converge as long as that piece is less than 1. So then I get the radius of less than 1/2. So actually, 8.6 is we're creating the power series, right? In 8.6, we're creating the power series. And I said to you, hey, make sure you do a couple where you just find the radius of convergence. But if you do go to 8.5, that's all it's asking you to do. It just says, hey, here's a power series, find the radius of convergence. So that's a good thing to do as well. So do some problems in 8.5, at least until you capture the three possibilities for the radius of convergence. If the limit is 0, the radius is infinite. Any radius will work. If the limit is infinity, nothing will work. Only works at the origin or at the at the center. And then of course like in this one, it's a finite radius, right? Some fixed radius. Good. One more problem, and then we'll take a little break. Okay. You feeling okay about this? What are the thoughts? Yeah. Okay. 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 Oh, better about it. Yes. It gets easier. Yeah. Yeah. You got to remember everything. Unfortunately, until you throw that hat up in the air, until you get your final grade. Believe me, in my undergrad, my last class was Advanced Calc 2. In Advanced Calc 2, we're proving everything in calculus. And I got a C in it. And believe me, I was just like, yes, I'm done with this. I can't stand. Yeah. It's a great feeling when you finish here and transfer. And then when you finish your undergrad degree, oh my God, it's incredible. I was so burnt out, I didn't go to grad school right away. It took me 15 years to go to grad school. But if you have the energy, go right to grad school, right? Get the master's at least. It does a lot for your paycheck if you have at least the master's. For me, I was so burnt out. I didn't want to go more school. I got a summer job in Baltimore teaching 6th graders calculus. This is called the Center for Talented Youth or something like this, if you heard of this program. So, and we had to take their books away from them when they went out to have a break or recess, because they would bring their books with them. They were such nerds. And I got duped into thinking I loved teaching because I had these kids that would never, right? They would do anything we wanted them to do academically. And then I started teaching in New York City, and I turned my back to write on the board, and they would throw shit at me. I had to learn how to write backward or. So anyway. All right, let's do a problem where we're going to use our Maclaurin series, right? This is what we did yesterday. So we're going to compare a Maclaurin series problem with Simpson's rule is what we're doing today. So Maclaurin versus Simpson. Now, for Simpson's rule, I want to keep it at 4, okay? Just because I don't want us to calculate too much. But I want to see how many terms of Maclaurin I need to get a better estimate than a Simpson 4, right? That's the idea. Let's just start real simple with it, okay? So let's start with, let's say the integral of 0 to 4 of e to the minus x dx. So real simple. Of course, we can get the exact, right? We can get the exact here. What is this? What is this integral? Yep. Nice. Right, so from 4 to, right, so when I put in the 0, I get 1, and when I put in the 4, I get 1 over e to the 4th, and that's enough. I could, whatever, right? All we want to do is see how close Simpson gets, and then see how many terms we need from Maclaurin to get even better. Yes, you with me? So I'm using my my dinosaur calculator here. .98. Yeah? We okay? Good, let's get our Simpson's rule. Let's get our Simpson with 4 partitions. Delta x is 4 minus 0 over 4, so 1, right? And we need delta x over 3. Let's see, we need 1 e to the 0 plus 4 e to the negative 1 plus 2 e to the negative 2 plus 4 e to the negative 3 plus 1 e to the negative 4. We agree? 1, 4, 2, 4, 4, 2, 4, 4, 2, 4, 1, right? We're looking for that 4, 2, 4 pattern. I'm sorry, 4, 2, 4, 2, 4, 2, 4, 2, 4, right? And then making sure we bookend with the 4s and the 1s, right? Everybody okay here? So I'm not going to bother changing anything here. I'm going to go right to my calculator. Pretty good. Yeah? Nice. Oh, sorry. It's taking me forever on this old school thing. Wow, yeah. Pretty damn good. So I'm going to leave it at 0.98. I'll say 0.987. All we need is enough terms from Maclaurin to be under 987, right? Or better yet, within 0.007 plus or minus of 0.098, right? So Maclaurin, first of all, we need, everybody okay here? Yes? So what we need from Maclaurin is we need, first of all, our series for e to the x, which is the sum of n equals 0 to infinity of x to the n over n factorial. Yes, I've got it memorized just because I wrote it down yesterday, but I'll forget it next week. You're going to put it on your formula sheet, right? Please. Or get the tattoo. I say if you are that dedicated to mathematics that you'll get a tattoo, it's not cheating, right? If you're You just gotta make sure you put the tattoo somewhere on your body that you don't have to take clothes off during the test. That's important. Yeah, yeah. It's a joke. I'm joking. I can get you fired for
I've
that.
seen that's a funny sketch about
Oh, really?
tattoos.
Oh, yeah.
It's like, you just like, you can't use your tattoos.
That's funny. People have asked me if you had a mathematical tattoo, what it would be? I say a decimal point. Because it hurts. I don't want it. Okay, so e to the minus x, what do we do? It's that simple. Is I'm going to replace, right, my placeholder for x with that new version, right? The input of my series with the new version of the input of my original function. So just putting in the negative x there. And then getting it into that form of negative, the sign, the coefficient, right? And the x term. I'm always trying to think of those three things: the sign, the coefficient, and the x term. So I'm integrating this, right? The integral of e to the minus x dx should be the integral of that series. And of course I could do it term by term, or I can just use the series itself. I want to make sure that you are trying both. Do it term by term and then collapse the series, or do the series and then expand the series. Right? Does that make sense, what I'm saying? So what do I get? I get the series from n equals 0 to infinity. The coefficients don't change, the signs don't change, but the x term, right? I got to add 1 to that and then divide by that new piece, new exponent. Because I'm asking you, right? Remember, we're doing this from what, 0 to 4? I'm asking you, how many terms do I need? I think once I get into pattern of writing out terms, I want to go with it. I don't want to have to come back to write out more terms and then evaluate, right? So I want to just start writing out terms. I have a feeling I could need up to 10. I don't know. But once I get the pattern, it's easy to keep writing terms, so it's better to maybe go a little bit more than what I possibly might need. So help me. Looks like my first term is just x. Do we agree?
Yeah, because that bottom part is just n plus 1 factorial.
Just n plus n. Oh, nice. Yeah, it is. Oh, that's even prettier. Thank you. That's great. I didn't even see that. You see how he's got n plus 1 factorial out of there? That's pretty cool. All right, what about for 1? When n is 1, what do we got? Yeah, negative, right? Yeah, negative. Over 2 factorial? Yep. So I can already see this, and I think that's true, but let me just make sure. When n is 2, I definitely get an x cubed, and then I get a 2 plus 1, a 3 factorial, right? Yeah. So that's pretty easy now. I don't have to think at all, right? But I'm bored, so let me just try 6 terms. What's nice, when I plug in 0, they all go away, right? So all I have to really do is plug in, right? So I'm saying, how many Maclaurin terms do I need? But when I plug in a 4, let's see, what do I get? 4 minus 4 squared over 2 factorial plus 4 cubed over 3 factorial. I'm going Desmos. It's too archaic there on that calculator. Am I doing something wrong?
Yeah, I'm getting a negative number two.
Hmm.
Maybe it's a really hard for the
Yeah, it looks like a lot of
factorial bigger than.
yeah. Hmm.
Yeah, okay. After,
How many terms?
after like the second term.
Nice. Almost. Damn it.
12 terms, I got 0.972.
Nice. Yeah, that one's already,
That's horrendous.
yeah, sucks.
No, we don't have to calculate the factorial.
I know. Thank God. Thank God we can use this on the test.
Got
There we go. 12 friggin' terms. That sucked. .973. Yeah.
For even
The key here is, and you have to realize what this Maclaurin series is doing for us. It's not ideal here. First of all, I can already do this integral. So why am I, right? Why am I doing Simpson's rule? Or we're just seeing, how we do here. But the Maclaurin series will do the ones that we can't do by hand, right? So, kind of like, well, is Simpson's rule better than Maclaurin? But I really see the simplicity in turning things into sums of polynomials, right? As opposed to this exponential function or whatever, we're dealing with. If I could turn everything into polynomials, it's really, really simple. All right, let's take a little break. Let's come back. Oh, that's even better.
Yeah.
Thank you.
I think we're gonna see it as we keep going, it's even better.
Yes, yes. So let's take a 20-minute break. So we'll come back at 5 of. Okay.